Rates and conversions can be tricky because they require us to expand our idea of what multiplication and division is. But that being said, once we get comfortable with it, we'll find out that it's no different in its operations than what we've been practicing for a while now. And it has a lot of added benefits that allow us to relate to different cultures, to empathize with different reference points, and to really be able to expand our understanding of certain things that we normally take for granted. So let's jump right in. Let's remember that math is a model of logic. So it's not about doing the correct operations in the correct way, but expressing something that makes sense to us on a deep personal level. So let's talk about why we're able to do something simple for our symbols, like multiply by 1. Why is this allowed? Well, multiplying by 1 comes from the story that those symbols represent. So we could think, for example, what is 1 times 2? Well, 1 times 2 is 1 time of 2. So we could think of that as drawing one instance of two things. Well, here's one thing and here's another thing. I'll make those each unit blocks. So one instance of those two things gives me 2 total. So that would be 1 times 2 is 2. 2 times 2 would have been 2 instances of that, so I would have repeated the pattern. But because there's no repetition, 1 times of 2 is just 2. Now this of course is very, very simple, but let's take a look at what we would mean if we said something like 4 centimeters. Now 4 centimeters is 1 centimeter, 2 centimeters, 3 centimeters, and 4 centimeters. So we could think of this as being 4 of these 1 centimeters. So 4 centimeters is 4 times of 1 centimeter. Or if we wanted to make this even simpler, it's 4 times of centimeters, which is exactly what we've drawn here. And that gives us some really interesting insight. Units are a multiplication phrase. So if I talk about having 5 miles, that's 5 times of miles. And if I talk about having 13 gallons, that's 13 times of a single gallon. Once we understand that units are just a multiplication phrase, it makes working with them so much easier because we can bring in all of the knowledge we've developed about multiplication, division, and fractions. Let's talk about this problem as an example. We have a snail that's traveling 12 centimeters in 4 minutes. So that's 12 centimeters in 4 minutes. That means that we could break this into groups of 4. So we could think about this as being a group of 4 here, and a group of 4 here, and a group of 4 here, where 1 of those centimeters in each group belongs to each of the minutes. So we could actually reorganize this entire thing, and we could label these 1, 2, 3, and 4, 1, 2, 3, and 4, 1, 2, 3, and 4, and show that we could get the same answer whether we draw 12 centimeters and divide them into groups of 4, or if we divide 12 centimeters, that'd be 4, 5, 6, 7, 8, 9, 10, 11, 12, and organize them so that we put all the centimeters that go along with the first minute together, and then the second minute can all go together, and the third minute can all go together, and the fourth minute can all go together. So we can think of 12 divided by 4 as getting us 3 groups, or we can think of it as being 3 centimeters in every minute. So let's now combine the information and the realizations that we've had. 12 centimeters in 4 minutes is the same thing as 12 centimeters traveled over 4 minutes, which is the same thing as 12 centimeters per 4 minutes. And all of these can be represented with the exact same fraction. You have 12 centimeters that are being split up and grouped depending on those 4 minutes. So 12 centimeters per 4 minutes is what we can start with as a piece of truth about this problem. Then it asks us, how many centimeters do we travel in each minute? Well, we could either go back to our picture here and recognize that that's going to be 3 centimeters that go along with each minute. Or if we want to start figuring out how to work with just the symbols, we can recognize that 12 centimeters over 4 minutes, each of those are unit statements, which is just multiplication. So this is 12 times of centimeters, and this is 4 times of minutes. Well, I can take the numerator and make that 4 times 3 times centimeters. And in doing so, I get an idea of looking at the bottom as 4 times 1 times minutes. And we know from fractions that if we have a numerator and a denominator that are the same thing and not 0, that we can simplify them away. 4 divided by 4 can be grouped off so that we're left with 3 centimeters per 1 minute. And those 4 times 4, or 4 divided by 4, is just simply 1. So that simplifies away to 1 time of 3 centimeters per minute. And if we want to simplify this down even more, we can recognize that 1 times anything is just going to leave us with exactly what we had. So 1 times of, we don't have to write the 1 times, we're left with 3 centimeters. And the denominator, we can get rid of that 1 times and see that it's just a minute. So 3 centimeters per minute gives us insight that we are traveling 3 centimeters for every 1 minute. Another problem where we get to recognize that just like the numbers, the units can also cancel. Now, if it asks how far does the snail travel in 3 minutes, we could of course use the picture here because we've recognized that each minute accounts for 3 centimeters. So I can sketch those off. So 3 minutes, we know, should be 9 total centimeters. We can count that off because each of these is a minute. So that would be 9 increments that's captured in 3 of those minutes. But let's play with the symbols. Let's see how the symbols behave. We know that we have 12 centimeters over 4 minutes. And that's because we've traveled 12 centimeters across 4 minutes. Now, if it asks, how far do we travel in 3 minutes? Well, that's another truth that we have. Let's write that down. We've got 3 minutes. We also know that the answer comes out to be 9 centimeters. So we just simply get to recognize that there's going to be something happening between the 3 minutes and the 12 centimeters per minute that produces the 9. Well, I don't see anything immediately obvious here. 3 plus 12 would be too big. 3 minus 12 would be too negative. So maybe we should try to rewrite our ratio in a way like we did for the last example. We'll write this as 3 centimeters per minute and recognize that those 3's turn into a 9 probably through multiplication. So we'll put a multiplication symbol here, and we'll double check that the 3 minutes times the 3 centimeters does in fact get us 9 centimeters, and that makes sense. So this fraction was just our way of dividing up the picture so that we could figure out how many centimeters there were in 1 minute. The 3 minutes that we're multiplying by is talking about how many repetitions of that chunk, 1 repetition here, 2 repetitions, and 3 repetitions of that chunk, that get us the total amount we're looking for. Now that we know that units are nothing more than fractions and multiplication statements, we can do a lot of these complex problems by just following the intuitive practice we developed while using fractions. So let's start off here. A snail again travels for 12 centimeters in 4 minutes. We now know that the 12 centimeters over 4 minutes can be written as a fraction, where I have 12 repetitions of centimeters, so there's a little hidden multiplication symbol here, and there's 4 repetitions of minutes, so there's a little hidden multiplication symbol here. So if it asks how many millimeters does the snail travel in 4 minutes, well, that's now interesting. I have the 4 minutes that I want, but I don't have millimeters. Well, let's do a little exploration. I know that 1,000 millimeters is equal to 1 meter. And I know that 100 centimeters is equal to 1 meter. I have, is it true that 1,000 millimeters divided by 100 centimeters is really just 1 meter divided by itself? And since I have something divided by itself that's not 0, that's really just a hidden number 1. So 1 is 1,000 millimeters divided by 100 centimeters. And this is a little bit odd. Why is it when I have two different things divided by themselves, I get a number 1? These don't look the same. But we remember, math is a model of logic. So it's not about how things look, it's about what they mean. And 1,000 millimeters is the exact same meaning as 100 centimeters. So when we put them on top and bottoms parts of the fraction, we're dividing something by itself, and that would be 1. So a really interesting consequence of this is that I can take this 12 centimeters per 4 minutes, which I know is a truth from the story, and if I'm allowed to always multiply things by 1 because it doesn't change the meaning, then what I can write instead is that 12 centimeters over 4 minutes can be multiplied by 1,000 millimeters divided by 100 centimeters. Now this is going to change its appearance, but it won't change the meaning because I'm only multiplying by the idea of 1, and multiplying by 1 keeps the meaning the same. So if we now work this through, we will get 12 times 1,000 is 12,000 millimeters. Millimeters. And then 4 times 100 is 400, and that would be, what? Oh, on the top, excuse me, I have millimeters, but I also have the centimeters. Let's carry that on for right now. Millimeters and centimeters. On the denominator, I have 400 minutes and the centimeters. We'll recognize that I have centimeters on the numerator and the denominator, so I can cancel that away, make that 12,000 millimeters divided by 400 minutes. And if we want to bring that down to 4 minutes, we can just scale it down by 100. So we'll make that 100 times 4 instead of the 400. And on the numerator, we'll make that 100 times, well, that would be 120 millimeters. So that the hundreds can cancel away, and I'm left with 120 millimeters divided by 4 minutes. Now, if you knew that there are 10 millimeters in a centimeter, you could have done this problem with that information as well. We could have, instead of relating everything back to 1 meter, started with 12 centimeters over 4 minutes, recognize that there's a hidden number 1 that we can always reveal. And instead of this 1, we could write down that there are 10 millimeters for every 1 centimeter. So on the next line, we would have 12 centimeters for every 4 minutes times, instead of 1, we'll write something that means 1. We'll write 10 millimeters divided by 1 centimeter. And again, since I have centimeters that are on the numerator and centimeters on the denominator, that's going to be something times itself, and they can cancel away. And that's going to leave me with 12 times 10 is 120 millimeters for the units. And then in the denominator I have 4, and the minutes is just the 4 minutes. Notice that sometimes we might get a little ambitious and we'll simplify these fractions too far. Well, this one, for example, could be thought of as 30 millimeters for every 1 minute. Well, that's fine, because then all we would need to do is scale up the number of minutes, and then we would be back to the proper number of millimeters. Or we could start a whole new problem where we start with the 4 minutes. We recognize that we could multiply that by a hidden number 1, and then that hidden number 1 could take the form of 30 millimeters divided by 1 minute, because that's how many millimeters I do travel in 1 minute. 30 millimeters is the same meaning in the story as 1 minute. Well, that's going to get you 120 millimeters after the minutes cancel away. Now there's one thing that we want to be careful of here. And so I'm going to take all this and I'm going to clear this all the way off. And I'm going to make a purposeful mistake so that we can recognize what it looks like. If we had started with the 12 centimeters over 4 minutes, and when we recognize that there's always that hidden number 1 that I can relate and I can change its appearance, there will be times when we will replace the 1 correctly, but it will not help us get our desired answer. For example, what if I replace this 1 with saying that there is 1 centimeter for every 10 millimeters? This is true. There are 10 millimeters in 1 centimeter, so this is still a proper number 1. But recognize that if we multiply this straight across, we will get 12 times centimeters times centimeters. And on the denominator, we will get 4 times minutes times 10, so I guess I can make that 40, times millimeters. Well, there's nothing to cancel away here, so we're left with an answer that is true, but not in our desired form. Whenever this happens, we want to go back to looking at how we replaced that number 1. But instead of writing our number 1 as the 1 centimeter over 10 millimeters, we'll write this as our 10 millimeters over 1 centimeter, so that we can plan ahead for how those centimeters are going to cancel away, and we'll be left with our desired 120 millimeters per 4 minutes. So let's put together everything we've learned. We're going to solve this problem in a few different ways, referencing the techniques that we've developed, and then we'll finish with a very elegant solution that you can use for all future problems. So let's start off with the fact that it says Boomer the dog eats 3.5 kilograms of food every week, and that we can always draw that if we'd like. So 3 halves would be 1 half, 2 halves, and then another 3 halves. So maybe I'll make 2 wholes that I split into half. That'll be 1 half, 2 half, 3 halves. That works out just fine. And the blank space is something that has not been eaten yet. And that's every single week. Now this asks how many grams, and I do notice that it says grams here, but it says kilograms over here, so I'll need to be careful of that. So it says how many grams of dog food will Boomer eat in 4 weeks? Well, this is 1 week, so I could take this and I could copy this 4 times. And then if we want, we could just go through and count this all up. We could just say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 halves of kilograms in 4 weeks. Which we'll keep off to the side and see that that is going to be 6 kilograms, right? 12 divided by 2, 12 halves is 6 per 4 weeks. So that's one thing we can use as a reference, but I want to start to avoid the pictures. They can be time consuming and they take up a lot of space. So instead, if we want to draw this as an equation, we could put this as 3 halves kilograms per 1 week. Now we were also given that we start with 4 weeks. So we have 4 weeks, which was a repetition of this 3 halves kilograms per week, and a repetitions are multiplication. So we can multiply this together and see that the 4 can be multiplied by the 3 halves, so we'll put 4 times 3 halves. And then on the numerator we have weeks, and we also have kilograms, so I'll just write that all in, because it's all just multiplication. And on the denominator, we have weeks, and then, well, this has a hidden number 1 on the denominator, so that would be 1 times 1 is 1 weeks. And since I see weeks on the top and bottom, I can replace that and cancel them away, and I can see that we have 4 times 3 halves, and we're only left with kilograms. And 4 times 3 halves, I can make that a hidden number 1. And 4 times 3 is 12. 1 times 2 is 2. And we keep our kilograms. That makes 6 kilograms that we found in the 4 weeks. Do we see how it's the same thing as what we had up here? But this is still kilograms. We need to make this into grams. And I know that there are 1,000 grams in every 1 kilogram. So take a look at how I can use all this information. I'm going to do it all from the very beginning, but I'm going to use one principle that lets us make this calculation nice and simple. I'm going to start with recognizing that the 3/2 kilograms per week is the same thing as 3 kilograms every 2 weeks. Do you see how that works there? 3/2 of a kilogram over 1 week means that after 2 weeks have gone, there's no longer 3/2 but 6/2. So 3 kilograms over 2 weeks. So I'm going to start with recognizing that 3/2 of kilograms per week could be made 3 kilograms per 2 weeks. Then I'm going to need to multiply that by 4 weeks, which we did above. And that if I'd like to get rid of the kilograms, I need to find some way of turning kilograms into grams. And I can do that by recognizing 1 kilogram is 1,000 grams. Now, since I organized all these fractions in just the right way, when I multiply them through, I'm going to be able to cancel this kilogram with this kilogram. I'm going to be able to cancel this week with this week. And if we multiply the numbers on through, we have 3 times 4 times 1,000 grams is going to be 12,000 grams. And on the denominator, I have 2 times 1 is just 2. So 12,000 grams divided by 2 is 6,000 grams. And that's our answer, which we can go back and double check makes sense as 1,000 more grams than the 6 kilograms we had figured out here and here. It's really important that we talk about how messed up the English system of units really is in comparison to the metric system. And this is something I like to stress because a lot of my students are American, and thus when they encounter things like millimeters and centimeters for the first time, it can be very intimidating because these words don't hold much meaning. But it's important that we recognize why they don't hold much meaning. It's not because the words inherently hold less meaning, it's because we grew up in a culture where we are simply familiar with a different system. But if we're allowing ourselves to step back from that system to really observe it as a third party, we're going to recognize that it's not nearly as good as the metric system. So for example, let's talk a little bit here. Think to yourself, what is a unit of length that is between a yard, which is something I can hold with my hands, and a mile? Is there a unit of measure that seems quite different? After all, when we start with an inch I can hold in my hands. A foot is enough that I can hold in my hands. A yard, I can hold that in my hands. A mile is so far that if I began walking right now, I probably couldn't tell you exactly when a mile ends unless I had something to help me keep track of my distance. And that's a very big leap in scale. In truth, there actually are units that are between them. They're just not popular for us nowadays. Every once in a while they pop up though, so let's talk about a few. We've got a fathom. We also have a shackle. We also have a cable, a furlong, a rope. Maybe you've heard of a furlong if you've ever gone to a horse race. These are all units of length that are between a yard and a mile. In truth, there are a variety of different measurements of length all across the English and American systems. Here's a map that I found that just describes a few of them, and we can see some really interesting points. Now, these units can be intimidating, I'll give you that, but in truth, they're only intimidating because they're different. There's not that many of them, there's only a handful. Here you can see there's six prefixes that need to be learned, and their order. But once you have those, the system is super easy to work with. So you've got kilo. Kilo means 1,000, like in a kilometer, right? You've got hecto, which is 100. Not commonly used, but good to be aware of. Deca. Deca means 10. And then you have deci, where all of a sudden we start to talk about 1/10. So that means that we're going through division, smaller units. And then we have centi. Centi meaning 100th. right? Just like a bicentennial is talking about after 200 years, centi refers to 100th. So we've got milli. Milli is going to be 1,000. So let's look at what a kilometer means. A kilometer, we already know, has a prefix of kilo, a kilometer. And so if we remember that kilo means 1,000, this must be 1,000 meters. And that's it. It's 1,000 meters. What about a kilogram? Well, that has a prefix of kilo, and we know kilo means 1,000, so that must mean 1,000 grams. Do you see how standard this is, where we're able to simply use the words that are in front of us without having to remember what they mean? This is much better than having to remember how many cups go in a quart, how many quarts go in a gallon, and whether or not there are more gallons. What comes after gallons, by the way? In truth, there are more units. We just don't use them very often. We've got tub and barrel. That's too much to keep track of, and it seems very arbitrary. Versus here, we've got a millimeter. A millimeter has the prefix of milli, and milli means small. So we've got 1,000, no, smaller than 1,000, 1,000th. So that'd be 1,000th of a meter. 1 meter split into 1,000 little pieces. Each of those pieces would be a millimeter. So you could write it as 1 over 1,000, or you could write it as 0.001 meters. And that's because that 1 goes right in the thousandths place. It means the exact same thing. So as one more last chance, let's contrast this to the English system. And again, the English system for many of my students is just familiar. But if we take a look at some of the things that we've just grown up knowing, we'll recognize that there are a lot of frustrations we have every day that we're just ignoring right now. Like, for example, let's take a look at lengths, right? How many inches go in a foot? We know that off the top of our head. How many feet go in a yard? Maybe we know that off the top of our head. How many yards go in a mile? That one's difficult to remember for a lot of people, and it doesn't often come off the top of our head. How many inches are there in a mile? Well, we would have to do a lot of multiplication. Versus when we were talking about the metric system, we just simply had to count up a few steps and say it was either 10, 100, or 1,000 for a difference. What about if we talk about volume? How many tablespoons go in a gallon? That's a difficult conversion to do because you have to go through multiple steps where each of those steps are not equal in magnitude. So the metric system is better. Yes, it's unfamiliar. Yes, unfamiliar things can be scary, but I encourage you, think about it as something that's worth pursuing. Because there's a reason why it came about as a result of the scientific revolution and why many engineers prefer it. Scientists also prefer it. So it's because it makes much more logical sense and it's easy to use when you're talking about difficult, big calculations. Now, the last thing I'm going to leave you with is something that you may not have known, and that's that America actually tried to convert over to the metric system before. In 1975, the US passed the Metric Conversion Act as a way of trying to slowly transition us to a metric system from our English measurements. Now, it didn't work, and most of us haven't heard about it, because there was a lot of fear and misunderstanding around what these different units meant. For example, if you go to the gas station and they've all of a sudden changed their prices to not be in terms of dollars per gallon, but to be instead dollars per liter, it made a lot of people very uncomfortable because they didn't know how many liters their car required, and thus they thought they were getting ripped off. Well, that's quite a bummer because most of the world uses the metric system and recognizes its uses. The fact that America is still delayed is something that is not a pride point for us. So I encourage you, learn about the metric system, learn about its advantages, so that if we get another opportunity as a culture to switch over into a metric system, maybe we can do so with more gusto and support those of our friends who don't necessarily understand what the advantages are. It really does make life much easier and saves us from having to remember all of these arbitrary conversions that we grew up just simply knowing, but not actually being able to explain.